So in this picture here, we see a couple triangles. We see triangle UWV, and we see triangle XZY. And the question asks what rigid motion or composition of rigid motions show that triangle UVW maps to triangle XYZ. And if we look closer at these two triangles, we'll notice that they have some markings on them about certain parts that are congruent. So it says that segment UW right here is congruent to segment ZX. They have the same mark on them. It says that segment ZY is congruent to segment WV. They have the same mark on them. And we also see an angle in here that's congruent. Angle YZX is congruent to angle VWU. And so the question says what rigid motion or composition of motions shows that these two map to each other. And we know that if they map to each other, that would be another way of saying that they are congruent to each other, that they are identical to each other. And so let's think about that. How can I make this shape match up to this shape using rigid motion? And well, I might think if these two segments are congruent, WV and ZY, then I probably need them to kind of line up to each other. Same thing with WU and ZX. I need them to line up with each other, and then I need this angle here to line up with this angle. And you might be able to look at this and realize that there's just one rigid motion that I need to perform. All I need to do is reflect this over a line that would be somewhere in here, all right? So let's call that line M. And if I just reflected this over that line, flipped it if you will, because sometimes I call a reflection like a flip, then what's going to happen is the point W right here is going to end up exactly where Z is. The point V right here is going to end up right where Y is. And the point U is going to end up right where X is. This is going to flip over onto this one. So it would just be simply a reflection is all we need. And this example here showing us that, hey, look, when I have these two segments in this angle, congruent to these two segments in this angle, we end up having two triangles that can be mapped to each other or that would be congruent. And so that's one of the two big ideas that we're going to be taking a look at in this section. So the example on that previous slide was just showing you what we would call the side angle side congruence criterion, or the side angle side theorem. And what it says is if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. Now there's a word in there that we do need to probably talk about, this idea of an included angle. So if I look at this picture over here, and I notice that I have two triangles, RST and XYZ, and I have segment, let's write this out. I have segment SR is shown as being congruent to segment YX, and I have segment ST that is congruent to segment YZ, and I have angle S congruent to angle Y. So I have three pairs of parts that are congruent between these two triangles. I have two pairs of sides and one pair of angles. But if I notice the location of where those angles are, that's important. That's because those angles are what's called included angles. They are what are called included angles in this picture. And to be an included angle, it needs to be the angle that is formed by the two sides that we're kind of concentrating on or taking a look at. So segment SR and segment ST, these two segments here, the ones with the markings, when they meet, they form angle S. So angle S is considered the included angle. If I look at angle Y here, it's formed by segment YX and segment YZ. It's the included angle between these. One way I think of it is if I were to only look at or maybe only sketch out these two sides, in doing so, in sketching out these two sides, I would be including the angle, because when I just include these two sides, I wouldn't have this angle here, I wouldn't have this angle here, because I'm not drawing this segment that helps make those two angles. If I were to just sketch out these two sides, my sketch would include this angle. And so that's called the side angle side congruence criterion. If I have two sides and the angle that they make on one triangle congruent to two sides and the angle that they make on another triangle, then that's enough to say that the two triangles have to be congruent. It's called SAS for side angle side. And an easy way to remember that is to notice that in SAS, or in side angle side, the word angle, or the letter A, is right in between the two sides. It's kind of sandwiched in between the two sides. Just like in the picture where we have SAS congruence, the angle is sandwiched between the two sides that are congruent on both triangles. So SAS is one of what I sometimes call the shortcuts that we can use to prove that two triangles are congruent. By definition, two shapes are congruent if all their angles and all their sides are congruent, if they're exactly the same size and shape, right? But if we can just have certain pairs of things congruent in triangles, then that's enough to say that the two triangles are congruent. And so the first shortcut, or the first kind of fast way of determining that two triangles are congruent, is that SAS theorem that we just learned on the previous slide. So that brings us to another idea, and it's called the corresponding parts of congruent triangles are congruent. It's usually abbreviated with these 5 letters, CPCTC. Corresponding parts of congruent triangles are congruent. And this idea says that, hey, if I know that these two triangles are congruent, if I'm able to find out somehow, either a set of instructions tells me that these triangles are congruent, or I'm able to find out somehow, I figure out that they can be mapped to each other and therefore are congruent, or I figure out that, certain parts of the triangles are congruent, and that makes the whole triangle congruent. If I know the triangles are congruent, then that would lead me to be able to say that every single pair of corresponding parts would be congruent. So in this shape here, let's start marking out what we know. It says that triangle ABC is congruent to triangle XYZ. And so by CPCTC, we would know that that means that segment AB right here, it has a matching part over on triangle XYZ. Segment AB must be congruent to a part of this triangle. Now, to figure out which part it's congruent to, I can either kind of eyeball it and try and figure out, okay, if I were to spin or flip or slide this thing over on top of this one, what would this side match up to? I could do it that way. Or the easy way is to look right up here and notice the order of the letters in this thing here called the congruent statement. So that is called a congruent statement. Let me just write that up there. That is called a congruent statement. And that has a lot of important information in it. It not only tells us that the triangles are congruent, but it will also tell us what parts of the triangles are congruent. For instance, segment AB that I've marked with my one line, it has to be congruent to segment XY, because AB is the first two letters here, and XY is the first two letters right there. So segment AB is congruent to segment XY. I would also know that segment BC is congruent to segment YZ. And I would know that because BC and YZ are the last two letters in each triangle's name in my congruent statement. Additionally, I would be able to say that segment AC here must be congruent to segment XZ. We can tell that either by process of elimination or the fact that AC is the first and third letter here, and XZ is the first and third letter in this one. So I would know that these three pairs of segments are congruent. But I could also look at the angles. And I could say that angle A, right here, and angle X would be congruent because they're the first letters listed in the congruent statement. I would be able to say that angle B and angle Y are congruent because they're the second letters listed in the congruent statement. And I would be able to say that angle C and angle Z are congruent because they're the third letters listed in the congruent statement. So what CPCTC tells us, or the corresponding parts of congruent triangles are congruent, usually I just say CPCTC, is that once I know that two triangles are congruent, then that would tell me that all of their corresponding parts would have to be congruent. So let's put those first two ideas to use in this example problem. It says, given that segment AB is parallel to segment CD, and that's what these markings right here are telling us, that they are congruent, and that segment AB is congruent to segment CD. So that's what these two markings are telling us. How can you show that angle B is congruent to angle D? So this is kind of an interesting question, and it's going to require us to apply, like I said, both things that we've learned so far in this video. And let me explain why. I'm going to look at this picture, and I'm going to notice that there are two triangles in that picture. And I'm going to ask myself, hey, are these two triangles congruent to each other? And so let me start by listing out the parts of those two triangles that I know are congruent. For instance, I know that segment AB is congruent to segment CD. Now that is a pair of sides, or sometimes I kind of put that a little S in a circle off to the side just to remind myself, hey, that's one pair of sides between these two triangles that are congruent. And then I'm going to start looking at and saying, well, what else do I know would be congruent between these two triangles? And, you know, one of my sayings, you guys heard me say it, is that every problem is a puzzle and every puzzle gives you clues. And the clues here are that these two segments are parallel. And I would start to wonder, well, why does it matter whether these segments are parallel? What have I learned about parallel lines or parallel segments that could help me prove that two triangles are congruent? And what I'd learned is that sometimes parallel segments that have a transversal intersecting both of them will result in some angles that are congruent. And if there's angles congruent between these two triangles, that would help me prove that the triangles are congruent. So what I notice is that, let me just kind of highlight for a second. I just want to highlight part of this picture. Okay, so I just want to highlight the two parallel segments and this transversal right there. And in doing that, what I might notice is that angle BAC would have to be congruent to angle DCA, because those are alternate interior angles. And since I have parallel lines, I would know from back from chapter 2 that these alternate interior angles have to be congruent. And now that's a pair of angles that are congruent between these two triangles. Okay, so I have a pair of sides and a pair of angles, and I've learned about SAS. And so I might ask myself, well, can I find another pair of sides that I know have to be congruent for some reason? And if I think about what SAS means, it's that the angle has to be between the two pair of sides. So if I look at this triangle, and I look at this other triangle, and I think about, well, what segment from this triangle would make this an included angle, and what segment from this triangle would make this an included angle, I might realize that the segment that I'd be looking for is actually segment CA on both, because segment CA would make this angle, it's kind of the other segment that I need to make this angle along with this segment. Segment AB and segment CA would make this angle. And it's also the segment that would help to make this angle along with segment CD. Segment CD and segment CA make this angle. And since it's the same angle on both triangles, I can actually say that segment AC is congruent to segment AC. I can say that that's true because of the reflexive property. And now that would give me another pair of sides that are congruent. So now I know that triangle BAC is congruent to triangle. Now I got to be careful when I write this next congruent statement, because I got to put the letters from the other triangle in the right order. I got to think, okay, for BAC, what parts of this triangle match up with B and A and C? And if I look at that, I might realize that, okay, BAC starts at one end of segment AB, goes to the other end, and then goes down the other side of the triangle. So what end of this segment corresponds to point B? And I would realize that that's point D. So that would be the first letter in this triangle's name. A is the vertex of this angle right here. So it's going to correspond to point C. So C is going to be my next letter in that triangle's name. and then that would leave A. And those two triangles are congruent by side angle side. And now if those two triangles are congruent by side angle side, now that means that by CPCTC, every other pair of parts on this triangle would be congruent. For instance, I would be able to say that this segment and this segment have to be congruent because they're corresponding parts. And I'd be able to say that this angle right here and this angle right here have to be congruent. But most importantly, I'd be able to say that this angle and this angle are congruent. I'd be able to say that angle B has to be congruent to angle D, and that's because of CPCTC.